All right, implicit differentiation. We want to distinguish between functions written in implicit form and explicit form. And then we want to use implicit differentiation to find the derivative of a function. The difference between implicit and explicit is simply this. An explicit function is written in terms of a single variable on one side of the equation. This right here is an example of an explicit function. Y is here, x is over here. This is a function of x. Okay? This is an explicit function. I can rewrite this as f of x is equal to 6x squared plus 3x plus 4. This is what we define as explicit. An implicit function is one that does not have clear delineation between the variables and cannot necessarily be solved for a single variable. For example, y equals 6x squared y squared minus 2y plus 5xy minus 7. Right? This right here is an implicit function. And it would be incorrect to write it as f of x, because this is no longer a function of x, it is a function of x and y. Another example of an explicit function, x squared plus y squared equal, did I say explicit? I meant implicit. X squared plus y squared equals 6. Yes, technically this can be solved for y, and I would get y is equal to plus or minus the square root of x squared minus 6. A lot easier, though, just to look at it as an implicit function and find the derivative. Here's another implicit function, 6x squared y minus 4y squared plus 5x squared y cubed is equal to 12xy to the 5th power. That's also implicit. These are functions that cannot readily have the variables separated out. So how do we go about finding the derivatives of these things? Well, the guidelines are on page 141 in your textbook. We want to differentiate both sides of the equation with respect to x. We're going to collect all terms involving a dy dx on the left side of the equation and move all other terms to the right side of the equation. Then we're going to factor out dy dx on the left side of the equation and then solve for dy over dx. Anytime I take the derivative of y in this case, I must multiply it by either a dy over dx or a y prime, because that indicates that I have taken the derivative of that function with respect to x. And then I'm going to have to factor that out. So keep that in mind. What is dy over dx? It just means differentiating the function with respect to x. That's it. Okay. Let's look at what's going on here. Let's say that I've got 3x to the 5th power. And I decide that I want to take the derivative of that. And I want to take that derivative with respect to x, d over dx. And instead of just dy over dx, I could write it as d over dx. However, the thing is this variable right here in the dx matches this variable right here in the 3x to the 5th power. Variables agree. So the derivative is simply 15x to the fourth power. And I don't need to do anything else. However, when I look at this right here, dy over dx of the following, 12y to the third power. Notice that this variable and this variable disagree. I can still take the derivative of 12y cubed, but since I'm telling you to take it with respect to x, I have to indicate that in my finished answer. So the variables disagree. So that means that I'm looking at 36y squared, but since the variables disagree and I have to indicate with what respect I took the derivative with, I'm going to write dy over dx as part of the answer. I could, if I so desire, write it like so. It does not matter. It means the same thing. Okay? When I write the answer as 36y squared times dy over dx, that tells me that I have taken the derivative of that function of y with respect to x. Okay? Which means that if I look at taking the derivative of the following function, notice that I have two terms here, one with an x term, one with a y term. This right here matches that right there. And you have to remember that this is going to apply to both terms. No, I'm not using the distributive property necessarily, but I am using the difference rule, right? The derivative of x squared minus 2y cubed is the same thing as the derivative of x squared minus the derivative of 2y cubed. However, both of those must be taken with respect to x. And so I have a problem right there because the variables disagree. So the first part means that I'm looking at d over dx of x squared. I've got a minus sign here. I'm subtracting d over dx of 2y cubed. As I said, these variables match, so I can easily take the derivative of x squared and get 2x. I'm going to subtract from that this one. And I note that the variables disagree. So I take the derivative of 2y cubed, which is 6y squared. But since the variables disagreed, I must indicate that disagreement in my answer. And that is the derivative. So I should put an equal sign in front of it. That's implicit differentiation. It gets a little more complex than that. Okay? For example, let's say that I want to find the derivative of the following with respect to x. I don't know, 12x to the fourth y to the fifth power. What do you notice about this one in relationship to the one I just did? Yeah, it's a product, which means that I have to use what rule? Which means I'm going to find the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor, right? So let's write that. Okay? This is going to be equal to the derivative of the first factor. In fact, you know what? I'm going to go ahead and not even worry about the 12 because that's a constant. So we're going to put the 12 out here. And we're going to multiply that by the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. And this is what I'm looking at. The 12 is just going to stay outside for right now. That variable and that variable, they match. They agree. So I'm going to be looking at simply 12 x to the, not 12, I'm sorry, 4 x to the third times y to the fifth. And I haven't had to do anything, right? I'm going to add to that x to the fourth, but notice that this variable and that variable disagree, which means when I take the derivative of that, I'm going to get 5y to the fourth dy over dx. I need to simplify that if I can. Which means this is going to be 48x cubed y to the fifth. 5 times 12 is 60. X to the fourth, y to the fourth, dy over dx. Now the thing is I was just asking you to take the derivative of this function. Most of the time, when we take implicit, or when we perform implicit differentiation, it's going to be on an equation, not a simple term or sequence of terms. So, let's look at this. Let's find dy over dx for 3y cubed minus 6x squared plus 2y squared is equal to 12. No, yeah, that'll work. Okay? The thing about this one is I can't easily solve this for y by itself. So I'm going to have to use implicit differentiation. Since the equation cannot be easily solved for y, use implicit differentiation. Okay. Now, each one of those terms you need to find a derivative of. So we're going to do d over dx. And I could put dy over dx, but really, in this particular case, since I'm finding dy over dx, we're going to look at d over dx. Because this whole thing has to have the derivative taken with respect to x. Okay? So I'm looking at d over dx of 3y cubed minus 6x squared plus 2y squared is equal to d over dx of 12. Now, it doesn't matter. I can put this all together, just, 1 d over dx and put parentheses around the whole thing. I don't necessarily have to break it up like this. But what I do notice is that this d over dx is going to apply to all three of these. Okay? So I could rewrite this as d over dx of 3y cubed minus d over dx of 6x squared plus d over dx of 2y squared, and we already know that that is equal to d over dx of 12. So this first one, I notice that the variables do not match. So my derivative is going to be 9y squared dy over dx. I notice for this one that the variables do match. So it's simply minus 12x. I notice for this one that the variables do not match. So it's plus 4y dy over dx. And it doesn't matter with which variable I'm taking the derivative of a constant is always 0. At this point, you need to collect your dy dx terms on the left and everything else on the right. So this whole thing is now going to be rewritten as dy squared dy over dx plus 4y dy over dx is equal to negative 12x. Notice that everything on the left has a dy over dx common to it. What did I do? That's a plus 12x. I was making sure you were awake, Jennifer. Factor out the dy over dx, and you get 9y squared plus 4y is equal to 12x. Solve both sides of this equation for dy over dx, and dy over dx is equal to 12x over 9y squared plus 4y. Okay? That's implicit differentiation. And we can do higher order implicit differentiation. I could ask you to find a second derivative. If I ask you to find a second derivative, that means I have to use what here to find that derivative? I have to use the quotient rule. Question. Once I use the quotient rule, this up here is going to become d squared y over dx squared. And I'm going to have some dy over dx's in there. Which means that once I do that, I've got to replace it with this dy dx. We'll get to that tomorrow because I don't have enough time to go ahead and do the second derivative of this function, which we will do. Okay? All right, before you guys go,